In this video, we're going to go over the last two functions or models, which are logistic models and cubic models. I think this is going to be pretty straightforward because it's very similar to what we've done already. But just to quickly review, we've seen one model that has 0 concavities. Alright, we saw three models that have 1 concavity. And then today we're going to see 2 more models that have 2 concavities. Alright, so obviously linear, that was a straight line that had no concavity. Okay, then with 1 concavity we saw exponential models, we saw logarithmic, and then we looked at quadratic. Alright, so all 3 of these have 1 concavity. Now the 2 that we're going to look at today have 2 concavities, which means they're going to have an inflection point, and those are logistic and cubic. Okay, and I think these are different enough that we're not going to confuse them, as we've seen some examples where maybe a quadratic and an exponential data might look very similar. Alright, so let's come back. We're going to start with logistic. Alright, so a logistic model is going to be in the form that we have here. Alright, now in our other models we've always used A, B, and C, but here we use capital L, capital A, and capital B for our coefficients. Okay, and this L here, you can think of this as the limit. Okay, so what is different about a logistic as opposed to a cubic is that a logistic function is going to have 2 limiting values. Okay, and then one of those is always 0, like an exponential function, and then the other one is going to be this number in the numerator, which we're calling L. Okay, now the other thing that's tricky about this equation here is, do you see how there is already a negative up here in the exponent? So it's AE to the negative BA. So we have to remember that when we're trying to pick off what our coefficient B is here. But as we just said, this is one of our 2 functions that's going to have 2 concavities, and if I change concavity, I'm going to have an inflection point. Alright, so if we see data that appears to have an inflection point, it's either going to be logistic or cubic. And what I'm saying right now is the difference between these two, we haven't seen cubic yet, but the main difference is that a logistic function is going to have 2 limiting values, whereas a cubic does not. So the first case that we have here is when B, so if that B coefficient that in the exponent there is negative, so I'm always going to have one of these, one horizontal asymptote here at 0, and then I'm going to have a second asymptote up here at this number L, whether B is negative or positive. Okay, now in the case where B is negative and I'm decreasing, I start off really close to this limiting value up here, and I'm concave down. Okay, and then I will have an inflection point at some point and change to concave up, and then get really close to this limiting value down here at 0. Okay, in our other case, when A is positive, this function is going to be increasing. So again, I'm going to have one horizontal asymptote at 0, and the second is going to be up at this number that's in my numerator, which we've been referring to as L. Okay, now if B is positive, I'm going to start off really close to 0, and I'm concave up, and then I'm going to have an inflection point, and then switch to concave down, and then get really close to this limiting value. Okay, And that's exactly what this notation that you see in the lecture note says. In this case where b is negative, that's my decreasing case. Okay, if I go to the left forever, I'm getting really close to that number in the numerator, which we see in that picture I drew right there. Okay, if I go to the right forever, then I'm going to get really, really close to 0. Okay, so similarly, for our case where b is positive and we are increasing, so this is my increasing case here. If I go to the left forever, I'm getting close to 0, and if I go to the right forever, I'm getting really close to that limiting value. In this first example we're looking at here, I want to first determine if I'm in the case where I'm increasing or decreasing. In this first case right here, I want to determine if I am increasing or decreasing. So I'm decreasing, so I'm going to look at my exponent here and try to pick off my b component. So let's say this is e. Now remember that our formula always has a negative here, so this is e to the negative. Okay, so if I wanted to write this e to the negative b, well, I don't have my negative there, so we can think of this as negative 0.466x. Alright, so if we rewrite it like that, it might make a little more sense that here b is negative 0.466. So this is going to be the case where we are decreasing. Okay, and if we want to list those two horizontal asymptotes, one of them is always 0. So that's the easy one. And the other one is going to come from our numerator right here. So that's our limiting value. So that's the upper one. So that would be y equals 3.143. Okay. Then in the second example we have here, again, I'm looking in that exponent to find b, and this one already has my negative in it, so I'm going to pull off that b component, which is 0.688, which is positive, so this is going to be the case where I am increasing. Okay, and the equation for the horizontal asymptotes here, again, one is always 0, and the other one comes from this numerator right here. So my second limiting value is going to be 2.458. Alright, so I think the first thing the directions that were a couple slides ago say is to mark the inflection point with an X. So if we look right here, I start off concave down, and then here I switch to concave up. So somewhere around here, I'm switching from concave down to concave up. Similarly for the second case where I am increasing here, and I'm concave up, and then somewhere around here, I switch to concave down. Okay, now this first example is decreasing. Okay, so that tells me this was the function where b was negative. So I think that was example A. So if we were to write this equation, we would get 3.143 all over 1 plus 2.251 e to the 0.466x. Okay, and for this case, when I go to the left forever, I'm getting really close to this limiting value here. But now I know what that limiting value is. It's the numerator. So when I go to the left forever, that's what this piece is telling me, I'm getting really, really close to 3.143. Okay, then when I go to the right forever, I'm getting really, really, really close to the x-axis, or 0. Alright, now let's look at this second case. So here, this is the case where I'm increasing. Alright, so that tells me this is the case where b is positive. Alright, so that would be example B above. So that is 2.458 all over 1 plus 3.331 e to the negative 0.688x. Alright, so in this case, when I go to the left forever, I'm getting really close to the x-axis, or 0. If I go to the right forever, I'm getting really close to that numerator, which is 2.458. Okay, we're not going to go through every example every single example in the lecture notes here, because we have done so many of these models by this point. I think once we see maybe one or two of actually going through and writing the model, we will have this. But what is important, I want to make sure everyone understands why we would pick the model that we did. So in this first example, we're not going to go through all the details of it, but I want to make sure everyone would pick a logistic model for these data. So these are the heights in inches of various NBA players in 2009 and 2010, and how many of the NBA players were taller than this specific height. So the first one here we have is 68 inches, and we see that 490 folks were taller than 68 inches, all the way up to 80 inches, where I only have one person. Okay, now here they aligned the data to how many inches over 68, which isn't terribly important for us, but what we want to see is this shape. So what I think is important is if you saw this shape here, where I start off concave down and switch to concave up. Alright, what is important for picking the right model is that you say, okay, this model has an inflection point. So I know it is either logistic or cubic. Okay, and then we say, well, are there limiting values? Well, yes, there is a clear upper limit up here of, well, the total number of players in the NBA. I couldn't go above that. And then there is a clear lower limit in this context of 0. Okay, so I guess if we got, how many people are taller than, 300 inches, we would get 0. So I think the context might help you understand that we're definitely going to have limiting values in this circumstance. So we would pick a logistic. So here we see that this function is increasing. Okay, and it has two concavities. So if we have two concavities, we're going to have an inflection point, which we saw. Okay, the function starts off concave down and switches to concave up, and that happens somewhere around h equals 10. Okay, now we're not going to go through the details of modeling this specific example. We're going to look at a different one, but I hope that everyone, if you saw this scatter plot, would go with a logistic model. Alright, I do want to take the time to go through this example, however. Alright, so here we have various years and the percentage of folks that have broadband internet service. So of those that have internet access, what proportion or what percent of those use broadband? Alright, so the first question we have here is, what does the context suggest about the end behavior? All right, this is kind of what I was getting at with the first example. From the context, we see that there is a clear lower limit. At some point, 0% of people had broadband before broadband was a thing. Okay, and then at some point, who knows, I don't know if we'll ever get there, but there is an upper limit of 100% of internet access is through broadband. So because of that, the context tells me that we might have a lower limit down here at 0, and then I might have an upper limit at some point of 100. Now we might not get exactly 100 when we do the modeling, but from the context, we see that there's limiting values there, so I would go with logistic because I have an inflection point and limiting values. So what does the context suggest about the end behavior? There is a lower limit of 0% and an upper limit of 100%. Okay, so because I have those limiting values and an inflection point, we're going to go with a logistic model. All right, so I'm going to look ahead here and see that I think we're going to need to align our data to years since 2000. All right, so let's see if we can do that. So years since 2000, this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so I want you guys to go ahead and pause the video if you need to and enter these data into your calculator. So in list 1, I'm going to have 0 through, okay, and then in list 2, I'm going to have those percentages that are given to me. Okay, and just to verify that I have these entered correctly, I want to look at that scatter plot. All right, so that looks like what we're seeing here in the slides. Great. All right, so we have aligned our data, and now we need to find this model. So from the fact that I have limiting values and an inflection point, I'm going to choose a logistic model. So as we've done for the last 2 weeks, I'm going to go to the Calc menu, and I'm looking for logistic. So I do not see it listed here, so I choose F6 for more options. And now I want to warn you that above F2 there's LOG. That stands for logarithmic. That's the one we looked at the beginning of the week. So I'm going to choose F6 again for more options, and then there's logistic above F1. Okay, now my notation here is slightly different from the calculator, but do you see how I have a little key at the bottom there, so I can make sure that I get this correct when I'm trying to figure out which coefficient goes with which one. Alright, so to write our model here, my limiting value C is 102.557. My A coefficient here in front of E is 7.464, and then my B coefficient up here is 0.529. Alright, so let's see if we can write this model here. Okay, so my, let's see here, let's use our B of T perhaps. B standing for broadband and T standing for time. Alright, so my equation here is 102.557 all over 1 plus that A coefficient is 7.464 e to the negative. Now remember, the negative is already in the formula, and then my B coefficient here is 0.529 to the t. Alright, and I don't know if it's clear from my sloppy handwriting, but that should be over all of that. Alright, now I need an output description, an input description, and a domain. So this equation here gives the percentage of internet users with broadband. Alright, so that's my output, where my input here, T, the stuff that I put in list 1, that 0 through 9, that was the number of years after 2000. And lastly, I need a domain. We had input information from 0 to 9, or from 2000 to 2009. Alright, so writing that model should be getting easier and easier as we've done this over and over for 2 weeks. What's new is we picked a logistic model. Okay, now if I need the 2 horizontal asymptotes, one is always 0. Okay, and now the second one would be our numerator right here. Okay, so my second one is going to be at y equals 102.557. Alright, and remember when we were talking before, we estimated that there would be an upper limit around 100%, and it turns out when we do the model it's slightly above 100, but I think that's believable there. Alright, now in what year would the model predict that 99.9% of residents with internet have broadband? Alright, so this percentage here that's given to me is an output. Okay, so this lets me know that this is going to be a solve problem. Alright, now I would not want to attempt to solve a logistic equation by hand. So we're going to do this as we have done many of these, where we're going to use the calculator to help us solve. So I'm going to choose F5 here to copy that equation into Y1. That way I don't have to worry about rounding error or mistyping something or any of that. So now that I have that in Y1, I'm going to go to my graph menu. Okay, and I have that equation in Y1. I'm going to choose F1 to turn it on. And then in Y2, I need my output, which is 99.9. Alright, now next I need to pick a window, so the context of the problem might help us. If I jump back here, we have not reached 99% in 2009, so I think it's going to be somewhere after 9. So that might help me pick my window here. I know it's somewhere after 9, so let's go shift viewing window, and let's go from maybe -1 to 20. Alright, we're going to draw this, and it looks like I see it, but if I didn't, I could go shift zoom auto as we've been doing, and then now that I can see that intersection, I should be able to find it. So I'm going to go shift graph solve intersect. Alright, and so I get a value here of t equals 10.663. Alright, so if this is the number of years since the end of 2000, you know, any sort of decimal would put me into 2001, so this would be sometime during the year 2011. Alright, and approximately what year did the percentage of residents with internet broadband increasing most rapidly? Alright. Now we're going to have to remember all the way back to section 1.2. Increasing most rapidly, that is an inflection point. Okay, if you remember those 4 quadrants of a circle we drew, where we're increasing most rapidly, decreasing most rapidly, increasing least rapidly, or decreasing least rapidly, those are our cases for an inflection point. Now we don't know how to find this exactly yet. We're going to have to estimate here. So if I use the trace feature, Now, when we get to Unit 3, we'll figure out how to find this using our calculus, but right now it looks like maybe my inflection point is somewhere around here, so I might say somewhere around t equals 3. Oh, and I probably need units up here as well. Okay, in this example, our output is the number of 1,000 computers that are infected with the virus, and our input is hours after the virus was initially exposed to these computers. Okay, and again, before I have even entered these into my calculator, I know that there's a clear lower limit of no computers and a clear upper limit of all the computers, which would be 10,000, or an output value of 10 for us. Alright, so take a second now and enter these into your calculator. And go ahead and pause that video if you need a little extra time there. Alright, once I get those entered, I'm going to view the scatter plot, and I get something like we have here. Okay, and again, I have those limiting values along with an inflection point. If you see, I start off concave up and switch to concave down, which it would be evidence for a logistic model. Alright, so first off, does the scatter plot indicate two inflection point, one or two concavities? Yes, two concavities, because we have an inflection point. Alright, now we want to come up with a model here. Alright, so to do that, I'm going to go to my calc menu. I'm looking for logistic, which I don't see here, so I hit F6. I'm not going to be fooled into thinking that that LOG there stands for logistic, because that's logarithmic, so I hit F6 again, and there's my logistic regression. Okay, so here we get a logistic model. Again, our limiting value is 10.000 or 10, which is what we thought, right? Because we have a maximum of 10,000 computers. So that makes sense to me. And then my A coefficient down here is 99.015, and then my B coefficient up here, which is positive because we're increasing, is 3.676. Alright, so let's see if we can write this model now. So we might call this, let's say, V of X, V standing for some sort of virus we have here. Alright, so my numerator is 10, and then I'm going to have 1 plus 99.015 e to the negative, remember the negatives in my formula, and then my B coefficient is 3.676 x. Alright, so that was the new part. The rest of the model, the output description, the input description, and the domain are similar to what we've been doing. So this gives the number of 1,000 computers, infected with a virus. Alright, and then X here is how many hours after the virus was detected. So let's say X hours after detection. Alright, and then my domain here, we have information from 0 to 2.5. Alright. Okay, so write the equations of my two asymptotes. Well, one is always 0. Didn't have to think about that one. And then my other is going to be the numerator in my logistic model, which is 10. All right, so according to the model, how many computers will be infected at 3 hours and 15 minutes? All right, this is an input, so this is going to be an evaluate problem. All right, so I just want to take V and I want to plug in my value there. Now, here's the tricky part. This is 15 minutes is part of an hour, but it is not 3.15. Okay, 15 minutes is a quarter of an hour, so this would be 3.25. Okay, so I am going to copy my equation into Y1. So I choose copy, highlight Y1, and choose execute. Then I can jump back to my run menu to evaluate this. So I'm going to go to variables, my graph variables, Y1, and then we're going to plug in 3 1/4, as we have done many times. So here I get that we have 9.99, was that 3? Nope, rounds up to 4,000 computers. Okay, so in the second question, how long would it take for the computer virus to infect 5,500 computers? This is an output. Okay, so this one is going to be a solve problem. So I am going to jump to my graph menu here, as we've been doing. I'm going to make sure that that equation that I just copied is selected, and then in Y2 I need to put my output. Now remember, my units are already 1,000 computers, so 5,500 would be 5.5 thousand computers. And I need to think about a window that might work for me here. Where are those data? 5 looks like it's going to be somewhere between 1 hour and an hour and a half. So let's go 0 to 2.5 here. So I'm going to set my viewing window from 0 to 2.5. Alright, and I'm going to draw this. I can do a zoom auto if I need, and then find that intersection. Shift, graph solve, intersection. Alright, so here I get an input of 1.304. Well, no, let me see. Is that round up to 1.305, I think? Alright, so this would be x equals 1.305 hours. Alright, and it does not look like I am going to have time in this video to go over cubic models, so we will attempt to squeeze that in next week. So the last model will be cubic, and we're going to talk about that next week because I am running out of time on this video.